Welcome back to Calculus AB. Today's topics 5.10, Introduction to Optimization Problems, 5.11, Solving Optimization Problems. So what is optimization? So one of the most common applications of calculus involves the determination of minimum or maximum values. Consider how frequently you hear or read the terms such as greatest profit, least cost, least time, greatest voltage, optimum size, least size, greatest strength, and greatest distance. Before outlining a general problem-solving strategy for such problems, let's look at an example for right now. So, started off. So, a manufacturer wants to design an open box having a square base and a surface area of 108 square inches. What dimensions should the box be in order to produce a box with a maximum volume? So, they're giving us the surface area has to be limited to 108. So, that's a limiting equation. And then we want to find the maximum volume. In order for us to find the volume of a box, all we have to do is just multiply all its dimensions. In this case, we have x times h. So the volume would be just x squared times h. And then the surface area of the box is going to be just all the sides, all the areas of the sides added up, right? And then here we're looking at, in this case, we have an open box, so there's no lid on this. So we have the base, which is x squared, right? The top is going to be open. And then we have four sides that are x times h. So plus 4 times x times h. And again, this has to be equal to exactly 108. So in order for us to be able to find the maximum values using the first derivative and then the second derivative, first we're going to leave one of these functions in only one variable. So because we have two variables, we want to make sure we can solve our equation or substitute one of our values into the equation, which is just equal to that. So we just have x, for example. So here, let's solve for h. We're going to subtract x squared from both sides. That leaves us with 4 times xh equals 108 minus x squared. And then we're going to divide everything by 4x. And then we just simplify a little bit more. So we're going to find that h is equal to, we have 108 divided by 4x gives us a total of 27. No. So here that would be our h value right there. So 108 minus x squared over 4x. And then from there, we're going to substitute back into this. We're going to replace that value right there. So we're going to be looking at v equals x squared times 108 minus x squared over 4x. And then from here, we simplify. So we have 4x. This x goes away with one of these x's. It makes it a lot easier. So 108 divided by 4 gives us 27 times x from the outside minus x times x squared gives us x cubed over 4. And then here, so that's our v. Now we want to find v prime so we can determine where we have a max or a min. In this case, we're looking for a maximum. So v prime, take the derivative of this, gives us 27 minus 3 over 4 times x squared. And then here, right, we want to determine where we have our critical values. So we set this equal to 0. And then we're going to start to solve for x again to find those critical values. So add 3/4 of x squared to both sides. We get 27 equals 3 over 4 times x squared. Multiply both sides by 4/3. We end up with x squared equals 36. So therefore, x equals, we're using just the positive one, right? You can negate the negative one because we're looking for dimensions of a box. So x equals 6, all right? X equals 6. And now what we want to do is that we want to find the second derivative in order for us to determine whether at whether the function v, it's either a max or a minimum at x equals 6. So if it's a max, it's going to be concave down, meaning b double prime should be less than 0. If it's a minimum, then v double prime should be greater than 0. So let's find v double prime first. So v double prime of x should be pretty straightforward. We just take the derivative of this one right here. And that's going to be negative 3 over 2 times x. And then we plug in 6. So v double prime of 6 equals negative 3 over 2 times 6, which gives us negative 9, which is less than 0. So that means that at x equals 6, we have a max, right? So this is a maximum at x equals 6. Again, the second derivative test tells us it's concave down because it's negative there. So that has to be a maximum. So now we want to figure out what's h by plugging in 6 in here. So let's do that quickly over here. So we're going to say h equals 108 minus 6 squared all over 4 times 6. And that gives us a total of positive 3. So now here, the dimensions of the box are going to be 6 by 6 by 3 inches. So those are going to be so in order for us to have the maximum volume with a limited surface area, the dimensions of the box have to be 6 by 6 by 3. And then there are many possible types of boxes with varying dimensions that yield different results. So this is the one we found, right? If we have 8 times 8, that gives us 88 right there, times 1.745. Same thing here, 5 times 5, and then 4.15. We have less volume, less volume, less volume. Again, this is the only one that gives us that maximum value. So guidelines for solving apply to minimum maximum problems. So now we're going to have a strategy. Identify all given quantities and quantities to be determined. If helpful, make a sketch. Write a primary equation for the quantity to be maximized or minimized. Reduce the primary equation to having a single independent variable. This may require the use of a secondary equation. Determine a feasible domain for your primary equation. And then again, determine the maximum or minimum value by using techniques discussed in the topics 5.4, 5.5. Note that this includes taking a derivative and finding the critical values and setting up a chart. So again, we can now use, like when we see the prime changing from positive to negative, when it changes from negative to positive, right? That tells us it's a critical value. So now let's look at example 2. Which points on the graph of y equals 4 minus x squared are closest to the point 0, 2? So again, we're identifying quantities to be determined. Let's make a sketch, right? So let's start off with a sketch. So the point 0, 2 is right here. And then our parabola is 4 minus x squared, so it has a y-intercept of 4. And then draw your parabola as usual. So we're looking for the shortest distance between the parabola and the point itself. So if you guys remember, the distance formula is equal to the square root of x minus x naught, and then squared, plus y minus y naught squared as well. So again, in this case, we have our initial values. We have x and y, and then we can just substitute those in there. So our primary equation will be d equals x minus 0 quantity squared plus y minus 2 squared. And then if you simplify that a little bit more, you're just going to end up with d equals the square root of x squared plus y minus 2 squared. And then our secondary, so this is our primary equation. Our secondary equation is going to be this one right here, y equals 4 minus x squared. So we're going to be using this equation to reduce the number of terms in our primary equation. Since this is already solved for y here, all I have to do is substitute for y right there. So let's do that right now. So d equals the square root of x squared, and then plus, in this case, 4 minus x squared, the substitution for y, plus, minus 2, squared. And again, keep simplifying that. We're going to end up with the square root of x squared plus 2 minus x squared quantity squared. All right, so that's our way. Now to find the derivative, just to make it a little bit simpler for us, we're going to get rid of the square roots. We're going to square both sides and then take the derivative implicitly. So in this case, we're looking at d squared, right? So if I square both sides, d squared equals x squared plus 2 minus x squared quantity squared. So again, now we're using the tools that we've learned before. In this case, we're using implicit differentiation, right? So I'm taking the derivative of this with respect to x. If I take the derivative of d with respect to x, I end up with 2 times d, using the chain rule, right? Times d prime equals, the derivative of this side is 2x, and then plus the derivative of 2 minus x squared quantity squared. Again, you have to use a chain rule, so this is going to be 2 times 2 minus x squared, and then times negative 2x, the derivative of the inside. Again, simplify one more step, so we still have 2d times d prime. So again, I'm taking the derivative implicitly. So if you guys remember when we did, if we did y, this would be just 2y over d, like dy over dx, right? So now here we have 2x. So we have 2x plus, or minus here, minus 4 times negative 2 gives you negative 4x. 2 minus x squared. Let's clean up that a little bit more. So it's going to give us negative 8x minus 4x cubed. So 2d times d prime equals 2x minus 8x minus 4x cubed. And then let me continue over here. So d prime, I'm going to divide both sides by 2d. So d prime equals, simplify the top, you end up with negative 6x plus 4x cubed, or minus 4x cubed, sorry. Minus 4x cubed over 2d. Now we have a common factor of 2 here, so we can clean that up even further. So that's going to give us negative 3x minus 2x cubed over d. And again, d is right here is the square root of x squared plus 2 minus x squared quantity squared. So I'm just going to resubstitute that. So d prime is equal to negative 3x minus 2x cubed all over the square root of x squared plus 2 minus x squared quantity squared. So here, if we want to find our critical values, right now we're finally able to get to our critical values, and that's when d prime is equal to 0. So when does the numerator equal to 0? So negative 3x minus 2x cubed equals 0. Again, you can factor this. We're going to factor out a negative x, and that leaves us with 3 minus 2x squared, or plus 2x squared. Was this plus? Yes, this was a plus 4x cubed. I'm sorry. So plus there, plus as well. Sorry about that. And plus right there. So we're going to factor that out. So that gives us negative 2x squared here. And then that's equal to 0. So x equals 0 is one critical value. The second one is going to be given by x equals the square root of plus or minus the square root of 3 over 2, right? Once you solve this 3 minus 2x squared for 0. And then we also want to look to see where d prime is undefined. Now, there is no x values in here that are going to make this undefined, even if this is 0 or even if this is 0, right? Because it's always going to be positive. So therefore, we have no problems here, no imaginary, no complex roots, or 0. So we're good. So we're just going to focus on these two values, or 3. And again, let's draw a number line so we know what we're doing. It's a little bit easier for us to see which ones are the mix, the max, and the mins, right? So on this side, we have the negative root 3 over 2. We have 0 here, and then we also have root 3 over 2. So again, we're checking the sign of d prime, right? Of d prime. So pick a number to the left of root 3 over 2. We can make it negative 2 just to make it a lot easier for us. to see whether it's positive or negative. So the bottom is always going to be positive, that's for sure. Whatever number you guys plug in at the bottom, because we have those squares right there, that will always make it positive. The top, though, if we do pick -3, we're going to, or -2, yeah, let's do -2. We're going to have -3 times -2. And then plus 2 times -2 to the third power. So that gives us +6. And then 2 times 8 is 2 times -8 is -16. So that would give us a negative number on top. So therefore, this is negative here. And then between 0 and -√3/2, we can do -1. So again, plug it on top. In this case, we end up with -3 times a -1 gives us +3. And then 2 times -1 gives us a positive on top as well. And then again, let's do 1 between these two. If I plug in a 1, -3 plus 2 gives us a negative. So it's negative right there. And then above √3 over the square root of 3/2, that's going to be, again, pick a +2. So that's going to give us a positive on top. So if we change from negative to positive, this is a minimum, right? If we change from positive to negative, that's a maximum. And then we have another minimum between at the square root of 3/2, because it changes from negative to positive. So we can say that the negative values occur at x equals plus or minus the square root of 3/2. And then if we do the substitution, right, if we plug it into this equation, if we plug it into that equation, we end up with our points being negative root of 3/2, comma, 5/2. And then your other point ends up being positive 3/2, comma, 5/2. Again, you have to plug in these x values into this equation to get those right there.